methodological generalization of the Collatz sequences to 1 plus 2k times n plus s sub k of n if n modulo 2k is not 0, and n divided by 2k if n modulo 2k is 0, with computational verification for k equal 1 up to k equal 20. Amar Hamdas, January 26, 2026. While attempts to prove the Collatz conjecture have so far culminated in the work of Terence Tao in 2019, which establishes almost all orbits of the Collatz map attain almost bounded values, several attempts have been made to generalize the Collatz sequences 3n plus 1, but many of them produce sequences that lack the essential structural properties of the original Collatz dynamics. Among these, the most promising known generalization is the one proposed in 2022 by Naouel Boulkaboul, which takes the form 3n plus 3 to the power k and leads sequences to converge toward 3 to the power k. In this work, we propose a new methodological generalization of the Collatz sequences based on a two-part transformation. 1 plus 2k times n plus s sub k of n if n modulo 2k is not 0, and n divided by 2k if n modulo 2k is 0. Here, s sub k of n is a correction function preserving the generalized singularity previously revealed in our earlier work. This revised formulation ensures that all rank 1 branch beginnings exhibit the generalized singularity in binary form. 1. Introduction. In the present paper, we do not attempt to prove the Collatz conjecture. Instead, we introduce a methodological generalization of the classical Collatz transformation 3n plus 1, building upon the structural findings of the singularity pattern described in a previous preprint. The goal is to define a generalized transformation that preserves the binary singularity and the convergent behavior of the original sequences while extending to a parameterized form. Initially, the generalization was defined using only the odd transformation 1 plus 2k times n plus s sub k of n. However, this led to the appearance of rank 1 branch beginnings that do not exhibit the generalized singularity. To address this, we revised the g sub k auxiliary function to n divided by 2k if n modulo 2k equals 0. This paper includes a computational verification across a bounded domain for k ranging from 1 to 20, confirming that the sequences exhibit bounded behavior and converge to 1, supporting the consistency and relevance of the generalization. 2. Reminder. In our previous work, we revealed a singularity for the 3n plus 1 Collatz sequence as follows. The singularity consists in having or reaching a term in the sequence whose binary form satisfies the following condition. All bits at even indices are equal to 1, and all bits at odd indices are equal to 0. In other words, the singularity term begins and ends with a bit equal to 1, and each two consecutive bits equal to 1 are separated by 1 bit equal to 0. Generalization of the 3n plus 1 singularity. We define a generalized singularity as having or reaching a term in the generalized Collatz sequences whose binary representation satisfies the following conditions. It begins and ends with k consecutive bits equal to 1. Each two consecutive groups of k consecutive 1s are separated by k consecutive 0s. The number of groups of k consecutive 1s is greater than or equal to 1. 4. Deduction of f sub k from the singularity. In the previous preprint, we defined the auxiliary function f sub 3 as follows. F sub 3 from the natural numbers to the natural numbers. F sub 3 of n equals 3n plus 1. Now, how can a term a that qualifies as a generalized singularity be transformed into a power of 2k by a single iteration of f sub k, which is the generalization of the function f sub 3? To achieve this, we simply add to the term a the quantity 2 to the power k times a, such that the resulting binary representation has a multiple of k bits equal to 1. That is, the structure of a and 2 to the power k times a must be aligned in a way that all 1 bits in the binary representation of a are complemented by 0 bits in the binary representation of 2 to the power k times a, and vice versa. A plus 2 to the power k times a equals 1 plus 2 to the power k times n, which equals a binary number consisting entirely of 1s. The addition of a and 2 to the power k times a gives a natural number with a binary form composed only by a multiple of k number of bits equal to 1. Now to transform 1 plus 2 to the power k times a into a power of 2k, all we need is adding 1. But we will expose later the real meaning of adding 1 to 1 plus 2 to the power k times a that we have used here. So we almost finished the definition of the auxiliary function f sub k for the generalized Collatz sequences as multiplying the odd term by 1 plus 2k, then adding 1 to the result, but this definition will be adjusted later. We have transformed a generalized singularity term a by just one iteration of f sub k into a power of 2k term, and we transformed the g sub k auxiliary function to n divided by 2k. Hall 4.1 Adjusting the f sub k function. 4.11 Reason why we should adjust the f sub k function. If we consider that f sub k is defined by f sub k of n equals 1 plus 2k times n plus 1, then let us take k equals 2 as an example. We will now examine the behavior of f sub k of n for n equals 1. The first 113 terms of the sequence are 16, 31, 156, 39, 196, 49, 246, 1231, and continuing in this rapidly growing manner until the 113th term, which equals 178,658,613,633,967,656. As you can see, the sequence seems to grow to infinity, and there is no trivial cycle as in the original 3m plus 1 Collatz sequence. For 4.1.2, finding the best alternative to the plus 1 part in f sub k. The adjustment of the function f sub k, which we have so far defined as 1 plus 2k times n plus 1, concerns only the plus 1 part. It will be made by replacing this part with the best alternative that satisfies the following 4 conditions. First condition, offering the ability to integrate the Collatz sequence 3n plus 1 for a certain value of k. Second condition, maintaining the occurrence of the plus 1 part in f sub k, which we previously used to transform 1 plus 2k times a into a power of 2k when a is a generalized singularity term. Third condition, there must be a generalized trivial cycle starting from 1. Fourth condition, preventing the generalized Collatz sequences from diverging to infinity in such a way that convergence to 1 remains possible. First, let a be a generalized singularity term, and let us apply the f sub k iteration. The result is a plus 2 to the power k times a equals 1 plus 2k times a, which is a binary number consisting entirely of 1s. We have that the 1 plus 2k times a part of f sub k gives a natural number whose binary form is composed only by bits equal to 1, and the number of these bits is a multiple of k. So the plus 1 part of f sub k will transform 1 plus 2k times a into a power of 2k with a binary form composed of the same multiple of k bits equal to 0, followed by a single bit equal to 1. So in the case of a generalized singularity term a, we have f sub k of a is congruent to 0 modulo 2k. That is to say, the plus 1 part of f sub k allows f sub k of a to be divisible by 2k. But in the general case, where n is not necessarily a generalized singularity term, we have n is congruent to 1 modulo 2, and 1 plus 2k is congruent to 1 modulo 2. So 1 plus 2k times n is congruent to 1 modulo 2, and by adding the plus 1 part we get f sub k of n equals 1 plus 2k times n plus 1, such that f sub k of n is congruent to 0 modulo 2. Thus, the plus 1 part of f sub k allows only to get an even term. We consider that the real meaning of the plus 1 part of f sub k is to make f sub k of n congruent to 0 modulo 2k. And we can justify this by the fact that when we make f sub k of n congruent to 0 modulo 2k, we are aiming to satisfy the fourth condition. Since any term not congruent to 0 modulo 2k, when multiplied by 1 plus 2k, will be divisible by 2 to the power pk, with p in the natural numbers, by adding what we call in modular arithmetic the smallest non-negative additive inverse of 1 plus 2k times n modulo 2k. And we represent it by the function s sub k. 4.111 Definition of the S sub k function. The smallest non-negative additive inverse of 1 plus 2k times n modulo 2k can be defined as the smallest natural number S sub k of n that we need to add to 1 plus 2k times n, such that the result will be divisible by 2k. In general, we have S sub k of n equals 2k minus the remainder of 1 plus 2k times n modulo 2k, then modulo 2k again. But since 1 plus 2k times n modulo 2k is always positive, we have S sub k of n equals 2k minus the remainder of 1 plus 2k times n modulo 2k. And since 1 plus 2k times n equals n plus 2k times n, then S sub k of n equals 2k minus the remainder of n modulo 2k. S sub k function statement. Let Q be the set of all strictly positive natural numbers that are not congruent to 0 modulo 2k. We can now define the function S sub k, which gives the smallest non-negative additive inverse of n modulo 2k, as follows. S sub k from Q to the set 1, 2 up to 2k minus 1. S sub k of n equals 2k modulo 2k. Now to 4.1.2, does S sub k satisfy the first condition? If k equals 1, then F sub k of n equals 1 plus 2 times 1 times n plus S sub 1 of n, which is 3n plus S sub 1 of n. S sub 1 of n equals 2 minus the remainder of n modulo 2, which equals 1. So if k equals 1, then F sub k of n equals 3n plus 1. And the second auxiliary function for k equals 1 will be n divided by 2. So yes, the 3n plus 1 Collatz sequence is integrated into the generalized Collatz sequences for k equals 1. So yes, S sub k satisfies the first condition. 4.12.33 Does S sub k satisfy the third condition? We have the following. For all k in the natural numbers, for all n in the natural numbers, if n modulo 2k is not 0, then the term following n is obtained by an iteration via the auxiliary function f sub k. And it is equal to f sub k of n equals 1 plus 2k times n plus s sub k of n, which equals n plus n times 2k, plus 2k minus n, which equals n plus 1 times 2k. We also have the following. For all k in the natural numbers, for all n in the natural numbers, if n plus 1 modulo 2k is not 0, then the term following n plus 1 times 2k is obtained via the second auxiliary function, and it is equal to n plus 1 times 2k divided by 2k, which equals n plus 1. So, from these two rules and taking 1 as the first term of the generalized Collatz sequence, we get the following sequence. 1, 2 times 2k, 2, 3 times 2k, 3, 2k times 2k, 2k. And since the term that succeeds the term 2k is 2k divided by 2k, which equals 1, we conclude that there is a trivial generalized cycle of the form 1, 2 times 2k, 2, 3 times 2k, 3, 2k times 2k, 2k. So yes, S sub k satisfies the third condition. 4.12.5 Does S sub k satisfy the fourth condition? By choosing the S sub k function, we are aiming to satisfy the fourth condition by preventing the generalized Collatz sequences from diverging to infinity in such a way that convergence to 1 remains possible. And to finally prove that S sub k is the best alternative to the plus 1 part in the F sub k auxiliary function, we need to proceed to a computational verification over a moderate range of the 1 plus 2k times n plus S sub k of n, if n modulo 2k is not 0, and n divided by 2k, if n modulo 2k is 0, to verify if for all k, all the generalized sequences tested converge to 1. 5. Computational verification over a moderate range of the generalized Collatz sequences 1 plus 2k times n plus S sub k of n and n divided by 2k. 5.1 Efficiency improvements of the algorithm. 5.1 Early convergence criteria. Let b be a strictly positive natural number such that b is greater than 1. Let the set 1, 2 up to b be the first b natural numbers. If all natural numbers in this set converge to 1, then any natural number that converges to an element of that set will also converge to 1. This reflects the idea that a sequence does not need to reach 1 to validate the conjecture. It is sufficient that it reaches a previously tested smaller value, which ensures it will eventually reach 1. To test the convergence to one of the generalized Collatz sequences for k in the set 1 to 20, we tested the following ranges. From 1 to 2 to the power 30 for k less than 6. From 1 to 2 to the power 29 for k equals 6. from 1 to 2 to the power 25 for k equals 9, from 1 to 2 to the power 25 for k equals 10, from 1 to 2 to the power 22 for k equals 13, from 1 to 2 to the power 19 for k equals 16, from 1 to 2 to the power 17 for k equals 18, from 1 to 2 to the power 16 for k equals 19, from 1 to 2 to the power 15 for k equals 20. We use the improved algorithm GC tester, but for k equals 2 and k equals 4, the GC tester detected sequences with 140 million iterations without reaching a lower value. So the program displayed a message telling us that we must use GC tester 2, which does not use the efficiency improvement. To use that program, we first searched for non-trivial cycles with a third program called non-trivial cycles. For generating the histogram, we used the simpler program histogram, which has no improvement and tests each natural number, odd and even. 5.2 hardware specifications used for computational verification. The computational verification was performed on a personal computer with the following hardware specifications. Processor, Pentium dual-core E5300, 2.60 GHz, 2 cores. RAM, 2.5 GB DDR2. Storage, 512 GB hard disk drive. Operating system, Windows 7, 64-bit. Compiler, Borland Delphi 7. To ensure that the program can handle very large numbers generated during the iterations of the generalized Collatz sequences, I chose the int64 data type. It allows for values up to 2 to the power 63 minus 1, which provides a wide enough range to test billions of natural numbers and accommodate exponential growth without immediate risk of overflow. The test for k equals 1 took 18 minutes. The test for k equals 3 took 10 hours. The test for k equals 5 took 11 hours. The test for k equals 7, 8, and 9 took 4 hours. The test for k equals 12 took 10 hours. The test for k equals 15 took 10 hours. The test for k equals 18 took 8 hours. The test for k equals 20 took 9 hours. 5.3. Data extracted each program. The data extracted by GC tester. Count, the number of natural numbers tested. Count 1, the number of non-numbers validated because they converge to 1. Data extracted by GC tester. 2 beg, the start of each of the 32 small intervals. Count, the total number of even and odd integers tested. Count 1, the number that converged to 1. Data extracted by non-trivial cycles. Each time it tests 100 natural numbers, it displays the value of k, the number of cycles found, and each following line contains the number of elements in the cycle followed by all elements. The program runs continuously. If no new cycles are found, the result can be copied into the graphical interface of GC Tester 2. 5.4 Computational Results Report. All generalized Collatz sequences for k in the set 1, 3, 4, 5 up to 20, except for k equals 2 and k equals 4, over the moderate ranges converge to 1. The GC tester detected no non-trivial cycle since no sequence exceeded 140 million iterations without reaching a smaller value. For k equals 2, the only non-trivial cycle with an element less than 3,000 is, out of the first 1,073,741,823 numbers tested, 145,959,493 converge to 1. That represents 13.59%. For k equals 4, the only non-trivial cycle with an element less than 3,000 is listed in the paper. Out of the first 1,073,741,823 numbers tested, 971,669,489 converge to 1. That represents 90.49%. Definition of the generalized Collatz sequences. We define the auxiliary functions. G sub k of n equals n divided by 2k for all n divisible by 2k. F sub k of n equals 1 plus 2 times n plus S sub k of n for all n not divisible by 2k. K is called the exponent parameter. The generalized Collatz sequence C sub k is defined by C0 is a positive integer. Cn plus 1 equals F sub k of Cn if Cn is not divisible by 2k. G sub k of Cn if Cn is divisible by 2k. 7. Conclusion. In this work, we introduced a methodological generalization of the Collatz sequence using the transformation 1 plus 2k times n plus s sub k of n and n divided by 2k. This generalization preserves the singularity structure, the trivial cycle, and bounded behavior. For all tested k except 2 and 4, every trajectory converged to 1. These results are empirical and motivate further theoretical study.